Charles Mangin is not content with the 6502 in his Apple II. He wants to run Intel 8800 code. Next, Charles Mangin will demonstrate a Altair 8800 emulator for his Apple II.
Thank you. Everybody hear me okay?
Yeah.
Good, 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 good. Okay, so this talk is, the title of this talk is called It's Turtles All the Way Down, Emulators Emulating Emulators, now with extra emulation. So the Apple II, the reason we're all here, is a fairly well-known, let's say a solved problem as far as emulating it goes. The documentation was fairly complete. The machine was a very popular machine, so there was lots of hardware to experiment on. And as far as emulating it goes, we've got an almost perfect emulated version of the Apple II. Not so much the GS and the later ones, but the original hardware and many of the variations. The ROMs have been dumped, and all those, like I said, all those problems have been solved. And so emulating the Apple II, for instance, on Windows in AppleWin is something that's commonly done. I mean, most of us have an emulator on our laptops or on our computers at home instead of hauling around an Apple IIc everywhere we go just so we can play Choplifter or work on some code, or just, you know, for nostalgia's sake, you fire up ProDOS and bang on it for a little bit. So this is obviously would be AppleWin running in Windows. That Windows environment could just as easily be running in a virtual machine on a Mac, for instance, because that's emulated. Windows is emulating on a Mac, and that's fine. And then if you want to go one step further, you could even emulate Mac on, say, a Linux desktop with something like Parallels. So we've got these layers of emulation lasagna here, and it's a pretty extensive stack, but it works because all those things are a well-known problem and well solved. But can we go deeper? The answer, of course, is yes. We can go deeper. Running on the Apple II is ProDOS, or DOS 3.3, or CP/M if you have a Z80 card, or if you have Pascal or one of the other environments and something like that. But what came before the Apple II? What could we emulate on the Apple II with the hardware that we have available, without any extra cards, without any extra stuff? Well, what came first was this guy, the Altair 8800. I have this is an Altair Arduino, which is a modern emulator reproduction running on an Arduino with all the associated blinking lights from the front panel of an Altair. It weighs about 2 pounds, whereas the original weighs something upward of 40, and has a big metal case, and is very hard to find, and they're very fragile and whatever. So I don't have one of those. I have one of these, and normally sitting in my office blinking lights like it is now. So you get the experience of the Altair without the actual weight. So again, emulation, but this time in hardware. Pretty cool. And luckily, this week, and I've already forgotten your name. Jeff. Jeff Adams brought some real hardware, a clone of the Altair called the IMSAI 8800. The first computer clone. The first clone, IMSAI 8080, that on the inside is very similar. On the outside, it uses different switches and a little bit different front panel, but for the most part, it's an S100 computer running on an Intel 8080, and you interact with it in much the same way in the base model with switches and blinking lights. So this is pretty cool. If you want to come up after, take some pictures, talk to Jeff about it. I'm volunteering you to talk to people about this because I don't know much about it. This machine is as old as I am, and preceded the Apple by a couple of years. And this, the Altair 8800, when it appeared on Popular Electronics front cover, was the inspiration for the Homebrew Computer Club to join up and learn how to build your own computer for your home. And you know, they were all talking about Altairs and building hardware for it and running software on it. Inside the Altair 8800 is an Intel 8080 running at 2 megahertz. The Intel 8080 has, it's an 8-bit chip. It has 6 registers, 6 8-bit registers, but they can join together Voltron-like and make 16-bit registers. It also has a movable stack pointer, so its stack isn't stuck at page 1 like it would be in the 6502. It has a very different instruction set from the 6502. And like I mentioned before, it's running at 2 megahertz instead of at 1. But in essence, it's an 8-bit chip. Takes 8-bit instructions, can address 8 bits worth of memory. And so I figured it would be possible to emulate this on the 6502. And I was right, because somebody did it for me. In 1979, this guy named Dan McCreary, I went looking to see if there was documentation on emulating the 8080. And I found it in the form of a program called Sim80 by Dan McCreary for the KIM-1. KIM-1 is a 6502 machine, basically a 6502 with training wheels. I actually brought one a couple of years ago and showed it here and kind of talked about the innards of it. And being that early on and being a training machine and something that people were trying to learn assembly language on and learn the basics of computers, a program that could emulate a totally different architecture on the same machine meant you didn't have to spend money on another machine to learn 8080. You could do it on your KIM-1 if you already had it. So that did pretty well as far as type in or punch in programs went on the KIM-1. And I found the source code for it on archive.org and documentation, and I set about porting it to the Apple II, but it turns out he beat me to it again. And he came out with Apple 80, published it in 1979, and the binary for this I got from Brutal Deluxe on a tape image, a cassette image, but no source and very little documentation. So I had to sort of backport or port the documentation for the KIM-1 version over to the Apple version, and the source for the KIM-1 over to the Apple version. I was able to disassemble the binary and relocate it so it ran under ProDOS, load from a floppy instead of a cassette, and was able to modify it and get it to run on the 2E, et cetera. So it wasn't just loading from a cassette on a 2+. And so I felt great about that. I was like, hey, I can run this thing, run 8080 code. It's a little weird because you have to modify your code to run at a certain address instead of being unmodified code. And this is the interface for it. And it shows you the processor status, the accumulators, the registers, the stack pointer, the current program counter, the current opcode, whether there are interrupts, and it even has a debugger, so it has breakpoints. That's pretty cool for something that's running Intel 8080 code on a 6502. But that's not the interface that I wanted. This is the interface that I wanted. So I wanted to make this and simulate that on the Apple II. And so being the low-res kind of guy that I am, this was the result. And so you see the array of lights, the array of switches, and the great big logo telling you what it is. And that's the interface for what I called Sim 8800, which is Dan McCreary's Apple 80. There's Sim 80 on the KIM-1, Apple 80 on the Apple II, now Sim 8800, which gives you an interactive, and as you punch in the letters, or the hex code 0 through F, it'll actually activate the switches here. And then when you click run, the little run switch will go. So it's animated, the lights light up just like it would on a real Altair, so a great simulator of an Altair in low res on your screen. I was stoked. And then I started wondering what else I could do. So there's Apple 80, the basis, and then there's the virtual Altair sitting on top of it, and it has about 4K of RAM, because that's what the original Altair had when it came from the factory into your hot hands, whether you assembled it yourself or bought it pre-assembled. 4K, Intel 8080, but again, can we go deeper? The answer is, of course, yes. But to do that, we would need some way to get stuff into the Altair and out of it, other than just blinking lights on the screen, because as cool as that is, you want to be able to type. You want to be able to do stuff as if you were sitting at a terminal instead of flipping switches, because even when you've got the shortcut of typing it in on your keyboard, it can get a little tedious. So from there, I built in 6502 a virtual SIO card, which is a serial I/O card from Altair. Very basic serial interface. I didn't have to worry about baud rates and high bits and low bits and things like that, because I was talking to the Apple and basically taking whatever character it spit out from the Altair and putting it on the screen. So the virtual serial interface, the Altair thinks it's talking to a serial board on port 0, and it sends a character out. Normally the board would do all the manipulation to turn it into serial pulses to go down a line, on a phone line, or what have you. But instead the Apple takes it and says, that's a character, I'm going to put it on the screen. And with that and 4K, I was able to get Bill Gates and Paul Allen's BASIC for the Altair running in the virtual Altair. So 4K of RAM, virtual Altair, BASIC as you would get it on a paper tape, loaded into RAM or in a ROM, and you can run it, put in commands, very rudimentary BASIC, and there's some pretty well-known bugs and limitations to it. But as you did it, you could see the lights blink, and you could flip the switches, and oh, it was so amazing. But I was stuck with 4K, and I've got all of this space, this great big chunk of contiguous space in the Apple II's 64K memory space. And I was hanging out down here, running up against the high-res page. Not that I was using anything in high-res, but I was limiting myself there, because I was loading in from ProDOS and didn't want to mess with anything with the loader that I'd written. So it was all kind of stuck down here with 4K. But with 36K to play with, I was able to get the virtual Altair with its new virtual I/O running with 32K. So 32K on an Altair back in the day would have been a lot. That's a couple of big boards that you jammed in, that you paid really good money for, and the chips would come off, and it was, we even had trouble with the one coming up from upstairs to downstairs. We had a one of the boards on Jeff's machine came loose, and it was failing its RAM test. So that's more like what the hobbyist would have. He would have a serial board talking to a terminal or a teletype, and 4K would be very limiting, so 32K kind of reasonable, and again it fits in that 36-ish space on the Apple II in that memory map. But he also usually would have floppy drive, because you got to get stuff onto it. And into the teletype would be great, typing things in, doing a bootloader every time, load that paper tape, that's boring. You want to have a 8-inch floppy drive to load your data in. So I wrote a little module that does that. It reads a 300 and some odd K file off of a ProDOS hard drive, a few blocks at a time into memory, and pretends that it's the interface, this DC-DD card on the Altair. So the Altair could now load things in from disk. And so we have this little tiny buffer for ProDOS that's loading stuff in from the disk image, the ProDOS hard drive image. Too many layers of emulation already. And it has a little buffer here That goes into this virtual disk buffer for the Altair, and that's 4K. That's basically one whole track, or one whole, is it a whole track? Yeah. Of the 8-inch floppy. There's the code for SIM8800, and then there's the 32K of RAM. And then there's a little bit down here that's reserved, and a little bit up here that's reserved. And I've basically chock full, and a little tiny slice that's free for future expansion. So we've got the 32K, I've got the 36K of memory pretty chock full at this point. And I can run really cool demos. I can run later versions of BASIC that needed 24K or 16K of RAM. I wanted more. So having never messed around much with higher memory space than 64K, I had to learn a little bit about page flipping when it came to extended RAM versus onboard RAM, and whether or not I could do what I wanted kind of depended on how contiguous the space was. So I had to pretend that I had 0000 to FFFF for the Altair to address, so that I didn't have to tell the Altair to do its own page flipping, because that was a whole other thing on the 8080. Because you could, but I didn't want to get there just yet. So on the Apple side, I sorted out how to copy my code and the buffers into both the high and low memory spaces. And this is the first 32K of Altair RAM, and this is the second 32K of Altair RAM. And so between the two, I have 64K of RAM in the virtual Altair. And so now it can run CP/M. What? 48K version of CP/M. This one's from Lifeboat Associates. It's a sort of an offshoot of the original one. But in the end, you can load in emulation, running the exact same code that you would get on your 8-inch floppy for your Altair, in emulation on your Apple II. So CP/M on the Apple II without a Z80 card. And that's pretty cool. Because in CP/M, you can run CP/M basic. And you can run your own programs. So we've got an interpreted language of BASIC running on CP/M, which is an operating system running on an emulated hardware running on the Apple II. And the answer is yes, we can go deeper, because with 64K of RAM and CP/M and a 330K 8-inch floppy disk and a serial input, we can run Zork. So Zork on CP/M and Zork on any of its platforms is running a Z machine, which is basically a virtual computer that they run Z code on, and you're typing commands into it to run Z code on a virtual machine in CP/M, which is an operating system running on an emulated machine in 64K of RAM on a machine that only has 64K of RAM to begin with, emulating a 2 megahertz processor on a 1 megahertz processor with only 2 registers, making up for the fact that it doesn't have 6 registers. And I think we've completed our emulation lasagna now. So we've sprinkled the cheese on top. And the source for all of this is on GitHub, on my GitHub at option8/sim8800. And it really is turtles all the way down. Because it's amazingly slow. Just the idea of running the 8080 code on the 6502 without any of the other emulation layers on top of it and any of the other code and stuff that you're doing, it takes about 300 cycles of 6502, and that's in pretty tight loops and code. Because I haven't handed this off to the experts yet, but I'm sure that they will find that the original author did a really good job of optimizing the code for the KIM 1 and then for the Apple II. It still takes about 300 cycles to emulate one 2 megahertz cycle. So the only way this is really usable is in emulation, in Virtual 2 or something else where you can crank up that CPU speed. So you've got Virtual 2 running on Mac, which could be running on Windows, which could be running on Linux. Running an Apple II at 16 or 32 or however many megahertz you can crank it up to in emulation. Emulating the Altair, running CPM and a Z machine, and running Zork. Any questions? Can you go deeper? Maybe. Because someone did mention to me this week a 6502 environment that can run on a Z80. So you could add another layer and in CPM emulate a 6502, but on an emulated Z80. But it was I think he said it was a Z80, not an 8080, and there's a whole layer of complications that makes it. The architecture of the emulator is such that it's extensible. I mean, I obviously extended it to do the things that I'm doing. So if someone were to take it and add the additional opcodes for the Z80 and the extra addressing modes and things, I don't know enough about the Z80 versus the 8080 to know what that would entail. But it is the sort of thing that could be done. So you could emulate a Z80 instead of just an 8080, which is sort of a subset. And so it's possible to go another layer deeper, but I haven't gotten there yet. In the back.
In that machine, it's possible one 6502 processor on that machine. You can run 8086, maybe 186, 286, and 386 in that machine, not all at the same time.
Right.
You can address 24 bits of address space in that machine. That the bus became IEEE 696, which became an industry standard. People were putting 386s in on the S100 bus before it became defunct and IBM won the game.
Right. What Jeff was pointing out is that the S100 bus, being as flexible as it is, the architecture is such that it can handle, or you can get 6502 and 8086 and up to 386 boards. Yeah, to go into the S100 bus. Luckily, I'm not emulating at that low a level to where I have to worry about the bus that it's on. I'm looking at the ports on the 8080. It has an 8-bit address that lets it essentially address 256 different peripherals, and so I've got the serial ports on 0 and 1, and then the floppy on 10 and 11 or whatever it is. But I'm not going so low level as to actually do anything on the S100 bus. So that would be another layer deeper, to where you're emulating the hardware to then put a processor into it. That's well beyond my abilities. And even writing Apple 80 or Sim 80 is probably something that would have taken me more than one KansasFest to KansasFest duration to do. So I'm glad that I found it, and I was able to do all the stuff on top of it instead of recreating that particular wheel. Because I would still be doing that, and that would be a great fun project, but I would probably be banging into a lot of limitations in my own abilities there. Any other questions?
So you said that your low-res interface to Apple 80 allows you to actually flip the switches and enter in the data.
Yes.
Can you show us a couple of those?
Sure.
Something you work through with it, make it the
Sure. Let me see if I can do it on here. While I'm doing that, is there any other questions from folks? I'll try not to sing. Roger Ragnar kind of took the trophy on that one. Let's see here. For not singing? Yeah, okay. Let's open up the latest version in Virtual 2. There we go. All right. So if I send PR number 5. All right. So this is my shell. This is my loader program before you get to the emulator. So I can choose the disk loader ROM. This is as if you're either punching in programs or loading a tape, and it kind of chooses which chunk of memory or which chunk of bytes to load into memory before it starts up the Altair. So for instance, here's, it's got micro chess, so you can play chess very slowly against a very slow, mediocre player from what I understand. He's still better than me. You can run Kill the Bit, which is what this guy's running, or you can do a couple of different versions of BASIC. So I'm going to run Kill the Bit, and then you get some instructions here. And so it's X to examine memory, 0 through F to toggle the 16 switches, X to examine the memory, N for next address and previous address, just like flipping the switches on the real Altair. So you can examine and deposit memory, adjust the byte, examine and deposit, etc. So here's the basic interface or the low-res interface for the virtual Altair. And so what we'll do is trace, and you can see the lights blinking, and should be very similar to what you see on the Altair Arduino down there.
So how do the lights correspond to the coding registers and PCs?
This set of lights, the top row of 8, is showing you the no, it's showing you the process counter, the PC itself. Or no, that's this. The top row of 8 is showing you the opcode that it's running. So the actual bytes at the address, which is represented here. So you'll see it, if it's slowed down, you'd see it 101, 1101, and it would build up until it gets to a loop and comes back. So this is the address that it's running at. And then this is the high byte of the address. And the code that's down here in the low-end memory is telling it to store or load an address into one of the registers. And that address is actually cycling through. And so you'll see this light is pulsing every time it accesses that high address. And so you see, as an output, basically, the lights going across. And so if I start hitting the switches here, you'll see the switches going up and down. And I've managed to mess up my kill the bit game already. So I've got 3 bits to kill. Oh, I got a bunch of bits to kill. So anyhow, that's how you would play Kill the Bit on this guy here. The next state that this would be in.
Wait, when you flip the switch, what is that doing exactly?
It is. Yes, it's being read by I/O port 0 as the byte that gets sent or read by I/O port 0 on the 8080 is this byte here. These bytes, if you were in, let's see, trace, let's see, maybe I need caps lock. Anyhow, if you were in the program entry mode, these bytes here, or these switches here, would indicate which byte you're putting into memory, and then also what address you're putting memory into. So I would, if I wanted to put something in at 1000, I would flip this switch up. I would flip the examine switch, and then it would show me what's currently in at 1000. Then I could put in my new byte, 101010, and put deposit, and then that set of bits would be deposited into that byte location in memory. And so all of that is doable in this interface in the same way that it was on the hardware. So you flip the switches, you hit examine, then you hit next, and you deposit, and deposit, and deposit, and you build your program that way. A few switches, and then you've got kill the bit. There we go. Any other questions? You guys are quiet. I'm not keeping you from dinner. Dinner's not for like another hour, so.
You said that the slowdown between Apple 80 was 300 to 1?
Something like that, yeah.
Yeah, about. If you go to the top of your stack as deep as you went, what is the total slowdown?
It depends on which opcode it is specifically, because some opcodes take a lot of paths, but it's between 300 and 400.
Some of the 8080 opcodes are 19 cycles long. I forget what the 6502 is, like 3 or 4, 6. Yeah, okay, so the 8080, some of them are 19 clock cycles long. Even though it's running at 2 megahertz, 19 clock cycles.
Well, and again, some of the operations are essentially 16-bit operations because it's working on 2 registers at once, and so emulating that takes a lot of gymnastics in the 6502 code just to do it, even if it may only take 5 cycles of the Intel chip to do it, of the hardware to do it. The code takes many, many more because it has to do the gymnastics that are not extant in the hardware. So if somebody wants to try this on real hardware and do a physical clock test to see how long it takes to boot CPM versus the emulator, then by all means spend your afternoon doing that. But I'm going to run it in Virtual 2 in the Command 3 mode and let it go as fast as it can. All right, anybody wants to come up and take a look at the Altair Arduino, flip some switches or whatever, that's fine. Please be mindful of the IMSAI, because that is literally an antique, and I'm sure that Jeff would not like it if one of those very delicate switches were to come off in someone's hand. So those are there for you to look at, but please don't touch the IMSAI. And if you want to get an Altair Arduino or other similar thing of your own, I can tell you where that is. You can order the kits, and it's real easy to solder. It's a lot of fun.
Oh, I don't know if you've seen, they just had a revision of the Altair.
I just saw it.
It comes in this beautiful blue box.
Yep. The one I've got is in a bamboo sort of box, but the new ones you can get in a more period accurate blue box, and I'm going to order the upgrade, so next year I'll have the one with the nice metal blue box. Let's see here. If you want, You can get it at, well, altairarduino.com seems to work. Altair Arduino, and that takes you to Add Water and Stir. addwaterandstir.com. Yes, Addwater is his last name. Yeah, Add Water and Stir. All right, thank you.